Welcome to Learn at Work, a webinar series by the journal Work. I'm Karen Jacobs, the founding editor of the journal, and I'll be the moderator for today's Learn at Work webinar. It's with great pleasure that I have our speakers introduce themselves now.
Thank you, Karen. My name is Dr. Gemma Milligan, and I will be presenting today with Dr. Joseph O'Halloran. We both work at the University of Portsmouth. I have been here for 13 years. Previous to that, I worked at the Institute of Naval Medicine, where my focus was thermal strain and heat illness. On coming to the university, my focus shifted into physical employment standards, in which I've been involved in developing standards for the oil and gas industry, the Coast Guards, the Royal National Lifeboat Association, the RAF, and also looking at the implications of ageing during that. Another part of my focus is job demands, and also I look into the area and work in the area of strength and conditioning. My colleague Joseph O'Halloran is a senior lecturer here in Biomechanics, and he has been with the department for 6 years. Previous to this, he was at the University of Limerick, and he specialises in looking at movement patterns. Specifically, one area that may be interesting to the listeners is his work with the fire and ambulance on extrication of a stable casualty from a car, with the focus on minimising spinal movements. This interest in movement patterns also leads him into the area of human performance and strength and conditioning. Joseph and I collaborate on a number of projects, including the one we're going to talk to you about today. But we have also worked together looking at ladder climbing, specifically the ergonomics of this and the differences between novice and experienced climbers. We've also recently just conducted an experiment looking at altering people's stride frequency out of that of their self-selected, looking at the efficiency when then carrying load. So what we want to talk to you about today is specifically a job task analysis for technicians in the offshore wind industry. And in terms of how we're going to structure today, we're going to look at an overview of job task analysis, and we're going to bring in some other literature. This paper, the Job Task Analysis for Technicians in the Offshore Wind Industry, formed part of a special edition that we compiled for the Physical Employment Standards International Conference. So I'm going to be talking about some additional articles that paired along with this. So if we look into a job task analysis, the purpose of conducting a job task analysis is to gather, organise, analyse and document job information in order to define worker specifications. In order to be able to do this, we require a job task analysis to identify those tasks which are classed as generic, and what we mean by this is that they're undertaken on a regular basis. We also then can class tasks as critical. Now this means that if they are not performed to the required level, performance, productivity, or the health and safety of employees and the public are potentially compromised. In identifying those tasks, we need to make sure that they are measurable and reliable factors. So can we determine parameters such as frequency, the loads that are lifted, the environments in which these tasks are being undertaken? And is this reliable in that they are the same every time the task is performed? The tasks identified need to be necessary for the safe and successful performance of work, and they need to be unable to be modified. However, if modifications come in, which often happens within jobs, then we need to revisit the task analysis to understand how this has affected the demands and the way in which the job is performed. And then finally, when we look at the outcome, this allows us to identify those tasks which are generic and critical to the job itself, identify worker requirements, and in which we're able to define the physical abilities involved in that job, And we're also able to look at the ergonomic parameters, specifically looking at whether the equipment meets the job task analysis or if any modifications can be made. If we briefly step back in history and we look at the number of physically demanding jobs out there, we can see that as we track these through history, even with the advancement in technologies, some jobs haven't changed hugely. And when we look at steel workers, we can see from the pictures in front of you that in the 1930s, the job doesn't seem to have changed much to now in the 2018. However, if we look at the pictures closely, whilst the jobs might be the same, the equipment in which they're using has ultimately changed aspects of the job, potentially the health and safety or the manner in which they have to manoeuvre around the beams. So just because the job has stayed the same, the way in which it's undertaken may have changed. If we look at another job, a very common job across countries and within different organisations is firefighting. Whilst the aim of firefighting is ultimately the same, how it's approached has changed over the centuries. With the advancement in technologies, firefighters can now stay in close proximity to the fire for much longer. This not only changes the physical demands, but also the thermal and mental aspects of the job, which need to be considered within the task analysis. So one of the key things we need to consider is whilst the aim of many jobs remains the same, how they are undertaken changes. And if this occurs, they must be revisited and validated to ensure that the task analysis is correct. Not only this, we need to consider if tasks are completed or jobs are completed the same across countries and within different organisations. If we take the example of the firefighters, do industrial firefighters work the same as your mainstream firefighters? But when we look at the applications of a job task analysis, we can see that it adds a fundamental basis to anything we go on to do. When we look at job design, using a job task analysis enables us to identify similar tasks that can be grouped into categories. These categories are then able to be grouped to then define the actual job. This allows organisations to think about staff sizes needed to complete those jobs and identify logical ways of cross-training. When we look at employee selection, and this is where the majority of my work has focused on, we can look at it forming the building blocks of a physical employment standard, meaning that we can base our employment strategies on the physical demands to undertake the job rather than any other parameters. As we look through progression testing, there are some industries where there is a pay for skills progression system in which employees are compensated based on their demonstration of skill mastery. The job task analysis list generated allows for logical groups to be made in which progressions can be seen. This can mean that we can provide written and performance tests that can be developed to ensure mastery of all tasks in groups and help with promotion. If we look at training design, job task analysis can be used to select certain tasks for training. It can set the skill and knowledge statements associated with the selected tasks and organise them into training groups. When we look at training program placement, we can use a job task analysis to develop written performance or self-assessment tools to help place current employees into the training program at the most appropriate point. And finally, job aid and procedure design. We can use the job task analysis to set our health and safety requirements. We can also look at it to determine what aids are needed to help the worker to undertake the job. So the first study I'd like to talk about that is available in the special edition of the work is a review of the methods to identify the critical job task undertaken by the emergency services. Now, the aim of this study was to determine if a standardised approach to identifying critical job tasks exists in the development of a physical deployment standard in emergency services. But the relevance of this paper to this discussion today is to really look at the methods that should be used in a job task analysis. What this paper did was it conducted a systematic literature review to identify the studies that have been undertaken within this area, and it looked at the methodologies that had been used. Ultimately, it came up with 22 studies that could be included. It looked and found that there were 8 methods that were consistent across these studies. These included the use of surveys, questionnaires, focus groups and interviews, facilitated expert judgment panels, the review of policy and doctrine, including training manuals and standard operating procedures, historical analysis, including health and safety incident reports, case law, observation and analysis of training exercises, jobs descriptions and performance analysis, and consultations with subject matter experts and stakeholders. One of the additional things that we do as part of our research team is actually have the team members undertake the task. What this allows us to do is fully understand the physical requirements needed to complete these tasks. Interestingly, when we look at the results of this study, we can see that the 2 methods that were most commonly used were job descriptions and performance appraisals and consultation with subject matter experts, with surveys, questionnaires and focus groups coming in a close third. But what I find most interesting and is a really important aspect of any job task analysis is that we do not rely on one method. We can see here that the majority of studies actually use between 4 and 5 methods. This helps cross-validate within the different methods that you're using to make sure that the job tasks you identified have been covered as fully as possible. I just wanted to highlight this as maybe some interest for individuals that they may wish to go and read. This is another article that is part of the special edition and focused on a job task analysis to describe the physical demand of specialist paramedic roles in the National Ambulance Resilience Unit. Nauru works on behalf of the NHS Ambulance Service in England, specifically in challenging pre-hospital scenarios. And the aim of this study was to not only conduct a job task analysis, but also assess the physical demands. So if you're interested in reading further, please refer to the journal. And that brings me onto the work that we're going to talk about today. And that's looking at a job task analysis for technicians in the offshore wind industry. Before I start this, I would like to acknowledge the Energy Institute and Global Offshore Wind Health and Safety Organisation for funding the work. I would also like to acknowledge Dan McKinley, Marcus Peters, Kate Harvey and Professor Mike Tifton, because without them, the data collection would not have been possible. The objective of this piece of work was to determine the most physically demanding tasks associated with offshore wind. Now, if we look at a bit of background into the offshore wind industry, since 2003, there has been a large-scale commercial development of offshore wind farms. When operational, the turbines are serviced and maintained by technicians who are typically responsible for testing electrical components and systems. They're also responsible for the mechanical and hydraulic systems, inspecting the exterior and physical integrity of the towers, climbing the towers to inspect or repair turbine equipment, collecting turbine data for testing or research and analysis, and performing routine maintenance on wind turbines and troubleshooting mechanical, hydraulic and electrical malfunctions. So with this in mind, excuse me, we started to undertake the job task analysis. Now, the job task analysis in the present study was applied to technicians working on operational turbines and did not include or apply to employees associated with turbine construction. It should also be noted that this job task analysis was conducted in the UK specifically, focusing on the Siemens SWT 3.6 turbine. The critical tasks included the most physically demanding activities associated with two groups of technicians. These were the service teams, which on average were made up of 3 technicians, the range of which was between 2 and 4, one of which will be classed as the team leader. And then the second set of teams was the troubleshooting teams, which comprised of 2 technicians. The physically demanding tasks undertaken by the technicians during a typical working day and in emergency situations were broken down into the component job parts, which were then described in terms of frequency, duration, rest periods, clothing ensembles, environmental conditions, and the methods of best practice for actually performing the task. The method used in completing the job task analysis included multiple methods as prescribed in the previous slides we discussed. So in which we looked at observations of technicians actually undertaking the task, we ourselves as the research team undertaking the task, reviewing operational manuals and the measurement of equipment masses and or dimensions, and finally the use of focus groups and subject matter experts. In doing this, we were also able to identify components of fitness, and these were categorised into 7 different areas. The first being aerobic tasks, and when we were referring to aerobic tasks, these are tasks which last for in excess of 4 minutes, and when they were being performed did not change in intensity. Anaerobic tasks in which exercise was intermittent and there would be high levels of stress placed on the body. Strength, which we looked at in terms of muscular strength, where individuals would perform one task, e.g. lifting a piece of equipment. Strength endurance, if that task had to be repeated multiple times without a rest. We then come on mobility, which determines the amount or range of movement around a particular joint within the body. Coordination, so for example, coordinating the upper and lower body to complete a task. And then finally, agility, in which individuals have to coordinate in response to a stimulus. When we talk about the subject matter expert panel, the subject matter expert panel comprised of 9 members of the offshore wind industry, who all had various experiences and job roles. The subject matter experts fulfilled at least one of the 7 criteria detailed in the table in front of you. Collectively, the 9 subject matter experts fulfilled all 7 criteria. These include experience in performing the tasks, performing these tasks in emergency situations, having a position of leadership, witnessing the task being performed in acceptable and unacceptable manners, and finally, witnessing tasks being performed using several different techniques. I'm now going to hand over to my colleague, Joseph O'Halloran, who is going to take you through the results.
Thank you very much, Gemma. Before defining the individual tasks within the jobs, we can look at the turbines themselves. On the left, you can see the transfer vessel arriving at the turbine. The turbines vary based upon make and model in offshore wind farms around the UK and indeed around the world. As Gemma has stated, the turbines assessed during this report are the Siemens SWT 3.6 turbines, but certainly the dimensions that I talk about may vary to other turbines that you're more familiar with. In many locations, the time the working day starts is tide dependent and varies throughout the shift pattern. Departure time may vary between 3 AM and 3 PM. In general, all wind turbine technicians work a 12-hour day. Either the day can be spent on one turbine or changing between turbines. It has been suggested by our subject matter experts that up to 3 transfers may take place. On more occasions, it is likely to be 1. A number of different shift patterns are implemented across the industry, ranging from a 4 days on, 4 days off schedule, up to a 14 days on, 14 days off schedule. During these shift patterns, bad weather days may mean wind turbine technicians go through periods of not working. Some organizations automatically stand down wind turbine technicians after 9 days of continuous work, and wind turbine technicians can stand themselves down if feeling excessively fatigued. On a working day, the transfer from the shore may take up to 3 hours, depending on the distance offshore, the sea state on that particular day, and the number of turbines that must be visited before a technician arrives at their particular turbine. Transfer vessels may carry up to 3 different crews. Most wind turbine technicians rest or sleep during this transport time from the shore out to the turbine. On the right-hand side of the screen, we can see the turbine divided up into sections, beginning at the bottom with the transition piece. Above that, we can see the coolant level, then the A2, tower, moving up to A4, the yaw, and finally the nacelle at the top. These various sections will be referred to as we discuss the tasks. The total tower height will again vary between 80 meters up to a maximum of 120 meters. Now we move on to tasks identified, and it's important to remember that these tasks are not the only tasks, but rather are based on the most physically demanding tasks of the occupation and affect both the physiological and physical components of the task. The first task identified in the job task analysis is the transfer from the vessel to the turbine. In the bottom left, we can see a calm sea state as the vessel docks. The crew will travel in groups of 2 to 4. If it is standard maintenance of the turbine, then the technicians will likely spend their entire day at that turbine before returning to shore. If it is a smaller troubleshooting job, they may have to travel to up to 3 turbines in a particular day. Prior to transferring onto the external ladder, the wind turbine technicians need to don a life jacket weighing approximately 2.3 kilograms. Appropriate protective equipment. Minimum requirements include safety boots, gloves, glasses, climbing helmet, high visibility clothing. In addition, they will have harnesses and attachments. In cases where sea temperatures meet the company's set criteria, such as sea temperatures below 12 degrees Celsius, or in some cases every transfer regardless of temperature, a sea survival suit may be worn. It is worth noting that subject matter experts stated that most wind turbine technicians go from a resting or sleeping state to donning personal equipment and climbing in very short periods of time without any physical preparation. The transfer time generally takes less than 2 minutes, but is dependent on the sea state. The make of turbine will determine the type of transfer. For some, this will involve walking along a gangway onto a ladder or stepping straight onto the transition piece. Other transfers where the vessel attaches to the external ladder will be affected by the sea state, and thus the movement of the vessel will affect the size of the initial step onto the ladder, the speed of this transfer, and the distance the wind turbine technician will have to climb. These components suggest a mobility requirement for wind turbine technicians to achieve hip flexion above 90 degrees. Subject matter experts indicated the initial 5 to 10 meters of ascent following transfer were the fastest, but then were preceded by a rest stage. The time taken for each wind turbine technician to complete the initial climb was no more than 2 minutes. The agility requirement we see on the video on the screen comes from the need to react to the sea state. In this case here, rather calm sea state, but this is not always the case. Currently, external ladders are vertical, with the majority using a diamond-shaped rung. In this next video, we can see some other factors which might influence the transfer. Although this video depicts the technicians descending the ladder back onto the boat, we can see the effect of the sea state. This video is still a relatively calm sea state. However, we can see the boat move up and down about 1.8 meters in this instance. This has an effect on the coordination ability of your wind turbine technicians and their mobility and agility when climbing onto the ladder. Other factors that will affect the nature and demand of the transfer onto the external ladder include the state of the ladder rungs, such as buildup of deposits or wet rungs, both of which can compromise hand and foot placement and increase the risk of slippages. We can see some rust on the side of the ladder there, which will also impact on transfer onto the ladder. In addition, the wind turbine technician may be feeling seasick following their transfer out onto the turbine, and their sea survival suit may restrict movement when stepping onto the ladder. The second task identified was the ascent of the tower. This was collected from subject matter experts, the researchers undertaking the task, and the operational manuals. The occurrence is similar to the transfer, with up to 3 times per day, depending on the specific task at hand. On many occasions, turbine technicians will take a lift up to the top of the tower. However, if for any reason this lift is not functioning, they will climb up the ladders on the interior of the turbine. The ladders are in 30-meter sections with a total tower height of between 80 and 120 meters, as stated earlier. There are no time constraints on the ladder climb, with the wind turbine technicians allowed to rest either at the bottom or top of each individual section, or even on the ladder itself. There is a stipulation on the ladder climbing component, with only one person climbing a section of the tower at a time. The other crew members will rest either at the bottom of that section or at the top, waiting to climb to the next section. Reflecting back on the fitness requirements of this task, it was identified that mobility, coordination, anaerobic, aerobic, and muscular endurance were key components. We can recall that these tasks are not the only tasks, but rather based on the most physically demanding. Climbing down the ladder was also considered, but not reported to be as demanding a task as climbing up the ladder. Both on the ascent and descent, all technicians will be attached to a safety harness, and depending on the particular company, may also have a climb assist harness attached to them. The third task identified was maneuvering through hatches. There are multiple hatches throughout the turbine. In particular, as we climb closer to the top, past the A4, to the yaw, and into the nacelle, subject matter experts reported having to move through hatches of various sizes and adopting positions requiring coordination and mobility to maneuver through these hatches. In addition, strength is a key component required for each of these single effort lifts in opening the hatches above them. On reaching the nacelle, service teams have a minimum of 10 minutes rest before beginning any other critical tasks. The time taken to complete the climb of the turbine suggests that this task requires predominantly aerobic and local muscular endurance capabilities. Now we move on to our fourth task identified. The subject matter experts reported that the most physically demanding task service teams were required to complete was both torque and tensioning, which can comprise approximately 20% of the time on a single turbine. This task can require service technicians to manually handle the tension heads of various weights used to tighten bolts in a variety of awkward positions whilst standing, kneeling, or seated, depending on the dimensions of the workspace. Measurement by the research team identified the heaviest torque wrench used at 7 kilograms, with the heaviest tension head measured at 19 kilograms. Subject matter experts identified this as a whole body task, with fatigue particularly accumulating in the shoulders, torso, and lower back. This requires technicians to have elements of strength, muscular endurance, and mobility to successfully undertake this task. The final critical task identified was the stretcher carry of a casualty. This is not a regular task, but is an essential or critical task, as Gemma has stated earlier, and is important to be able to complete for the safety of the workers. Subject matter experts have identified 4 tasks when moving a casualty: hauling a casualty up the turbine, lowering a casualty down the turbine, extracting a casualty from the hub, and extracting a casualty from under gearboxes or generators. Of these, they have identified hauling a casualty up the turbine to be the most physically demanding task. All wind turbine technicians have completed a global wind organization Working at Heights course. This will allow them to complete all casualty rescues that do not require a stretcher or spinal board. For incidences where a spinal board or stretcher are required, individuals must have the Advanced Rescue Certificate. The hauling for wind turbine technicians, if an automated system is not available, is a standard 6-to-1 pulley. The maximum distance that each of these will move at a time is 4 meters. Therefore, this must be considered the minimum distance a wind turbine technician will be expected to haul a casualty, although in some cases this may have to be repeated multiple times as we move up through the turbine. The mass of the wind turbine technician population will vary, but there are weight restrictions applied due to the maximum loads the climbing kit can withstand. The total load is 136 kilograms, which includes the spinal board, thus making the maximum load of an individual 127.2 kilograms. This load is based on the cab lock system used by subject matter experts in this critical task analysis. This extremely demanding task will require multiple components of fitness, including mobility, coordination, anaerobic fitness, aerobic fitness, muscular endurance, and muscular strength. This concludes the 5 tasks identified during this job task analysis.
Thank you, Joseph. That just leads me to finish up with the discussion, where this project is leading to, and then some key take-home messages. So this was the first study to identify tasks considered physically demanding and critical for technicians working in the offshore wind industry. As Joseph detailed, there were 5 tasks identified to be the most physically demanding. These included the transfer from the vessel to the transition piece, ascent of the internal ladder, manoeuvring through hatches, torque and tensioning, and hauling a casualty up the tower. It is proposed that the identified tasks require a range of physical attributes, including mobility, upper and lower limb strength, strength endurance, aerobic and anaerobic capacity. If we look at a couple of the critical tasks in more detail, specifically that of ladder climbing, this actually yielded conflicting results in regarding the method of best practice to perform this task. Subject matter experts reported that technicians climb a ladder with 2 points of contact. This was also observed when looking at the videos. This is in contrast to the directive from the Health and Safety Executive, with the guidelines of safe use of step ladders and ladders, which advocates 3 points of contact. It should be noted that these guidelines appear to be for those free climbing, not those attached to a fall arrest harness. Similarly, though, the good practice guidelines for working at height in the offshore wind industry state that the probability of falling can be minimised by limiting the activities that are carried out from a ladder and ensuring that users maintain 3 points of contact. Therefore, the method of best practice used by the technicians to climb ladders requires some further investigation. In order to quantify the physical demands of these tasks associated with the offshore wind industry, there would need to be an agreement on the minimum acceptable operating procedures whilst using the methods of best practice for tasks where a load and repetitions could not be identified objectively within this study. It was not possible to determine the method of best practice, or in some cases, the minimum performance standards for all tasks presented. For example, due to variations in turbines, standardising certain tasks, such as transferring from the vessel, is extremely difficult. Further analysis that was beyond the scope of this project would be required to assess the impact of various ladder conditions brought about by the environment, for example, wet slippery rungs, on the demands of transferring from the vessel. Also, the impact of sea state on these physical requirements with transfer onto the ladder requires more investigation. In terms of orientation and the forces required to lift hatches, again, more investigation is needed. When we look at exercise or tasks, such as torque tensioning, this can be seen as a common manual handling task and as such would fall under the Health and Safety Executive Guidelines on getting to grips with manual handling and the rapid entire body assessment REBA, which would ultimately set the performance standards for any physical employment standard that may follow. In terms of the next steps, what we looked at here was wind turbines in the UK. We also looked at one specific model. Therefore, to validate this, we are in the process now of looking at a wider scale job task analysis to include multiple organisations across UK, Europe and the rest of the world. This will enable us to establish job task analyses and specific critical tasks and to see if there's any variation across industries and countries. What this will enable us to do is to measure and determine the physical demands being placed on workers, not just on one turbine, but on multiple turbines. This leaves us with a few take-home messages. Hopefully from this presentation, you will be able now to understand the various methods and procedures of a job task analysis. To ensure that a job task analysis is comprehensive and valid, we should be using multiple methods in determining the tasks involved. In doing this, we not only have to look at the task, but the interaction with equipment, environment, and techniques. This allows us to build up a comprehensive idea of the tasks involved within the jobs and ultimately determine worker requirements. But if any part of the job is changed or any modifications made in terms of the environment in which it's being undertaken, the equipment used, or standard operating procedures changed, then the job task analysis should be revisited. The reason for this is that it is the fundamental building block to any further job design, job training, or physical employment standards. We have included a reading list or a reference list for you to have a look through, but that just leaves myself and Joseph to thank you for listening, and we will open the floor to any questions if there are any. Thank you ever so much for listening.
Thank you so much. This was so interesting. And if any of our attendees, and there's quite a few, have questions, please type them in where it says questions, and I will ask our speakers. Thank you so much. And I want to start off with a question. This was so very interesting and, you know, applicable around the world for what you're doing. What is your next step? What would you like to do in this area? What's bothering you that you want to continue investigating?
I think one of the key things is there's a lot of job task analysis being undertaken that then inform current practices, whether that's job design, being placed on the worker. Also, another area, we tend to focus very much on the physical rather than the physical and the mental kind of strain placed on workers. And I think job task analysis should be used to get this multidisciplinary approach.
Fabulous. How about something on a global level? Do you see how your work will have an impact on a global level?
So this is an interesting thing, especially with job task analysis, because it's so specific to what we're doing. We can look at the methodologies that are being used, especially within this work, and setting it as, say, best practice going forward. But in terms of specific job task analysis, I think it's just important to highlight on a global level that if it's been identified on one specific, for example, turbine in this case, and it then goes through in the UK, is this actually the same within different turbines or within different organisations doing the same job. And I think job task analysis on a global scale can actually help identify where there are differences and then how we can get global standard operating procedures that maybe optimise the health and safety of our workers.
Great, great. I'm looking to see if we have any questions. If anybody has questions, please post them as well. We have quite a few people in attendance. David, Debbie, Lucinda, and Renee, if you have questions, please let us know. So I love asking this question. I hope you'll be fine with it. If the news media picked up on this, what could be the headlines and what do you think they would focus on as important to let the general public know?
I think that's a really good question.
You like that question? I love it. I actually ask people on their dissertation to answer the question. I'm glad you like it. Sometimes they don't.
No, it's a really good question. I think for me, it would probably be the extreme working conditions of people undertaking these tasks offshore. I think sometimes we underestimate just what impact going offshore, working in turbines has. And there's lots of videos you can watch online of where transfers go wrong, of how these turbines actually move in extreme weather conditions. And I think the tabloids would more pick up on these are extreme tasks in a extreme environment. And I think possibly they would go down more that route in saying our offshore workers have high physical demands and there's a high level of fitness going forward.
Great response. I'd like to see that as a headline.
Yeah, possibly.
I'm looking to see if there's any questions here. So the future, you talked about the future, but what about you individually? You know, what's that next big exciting project that you'd like to do individually or collaboratively? Is there perhaps a missing profession that you'd like to begin working with as well?
So we've got lots of exciting projects going on within the university. We're quite a multidisciplinary team, so we cross over quite a lot. We have some exciting projects with the military starting. Joseph and I have a particular interest in looking at altering, if we confine how people work and it's not within their preferred working movement pattern, how does that link into increased injury, and how can we kind of optimize and minimize kind of worker kind of differences in movement patterns to minimize their kind of injury kind of potential? I think that's an area that we're really interested in. Joseph?
Yeah, and I think that in some instances, some jobs require workers to work in conjunction with others. So they're forced to work to a pattern that other people dictate, or they are following their patterns. And that mightn't be the most economically advantageous position for them. And it might also be one that leads them on the road towards injury. And we're looking at, if you are forced into a movement pattern that's outside of your comfortable movement pattern or your preferred movement pattern, how your body reacts to that. So how the movement patterns change in response to other people's movement patterns. And there's some industries around the world that this is particularly prevalent in. And we can look at this from both a performance perspective, so the energy cost of working to somebody else, or from an injury perspective and helping to prevent these injuries occurring.
One of the other, sorry Karen, one of the other areas we're both particularly interested in is when you look and you work across different industries, one of the things that come out as the most physically demanding task time and time again is emergency response duties. So responding to incidents and casualty handling and casualty evacuation. And I think what Josie said there about kind of optimizing working patterns and how we minimize the effect then on the casualty is something else that we're both really interested in.
Fabulous. Well, we're very fortunate to have you both being interested in this. It's so very important to worker health. So I don't see any questions posted at this point. Are there any concluding statements that you'd like to make at this point?
Just really to say that this work is ongoing, and we hope within the next 18 months to 2 years to have an international critical task analysis done specifically on these areas. And also just to highlight the special edition that we did for you following on from the 3rd International Conference on Physical Employment Standards, that has a lot of interesting articles around this area, such as the ones I presented on the literature review and also the Nauru. But there's also a number of really interesting articles in there on physical demands, on physical employment standards, and optimizing performance.
And I have to take it back. We do have some questions, so let me I take that back. Let's see. The first one was, excellent webinar. Were employees required to be able to swim as part of their job? And was a recovery of a colleague from a fall in the sea considered to be a critical task? So that's one, and we've got a few more.
Okay, so that's an excellent question. All of the technicians wear life jackets, so it's not a known requirement of them to be able to swim. They are all wearing sea survival suits. The rescue of them would actually fall down to the vessel crew, who were not actually considered within this task analysis.
Yeah, so and some employers require the sea survival suit to be worn throughout the turbine. Most required to be, or allowed to be taken off during the transition piece. So the sea survival suit would certainly be in place from the shore all the way to the transition piece for everybody, and then depending on the particular employer, may or may not have to be worn beyond that point for the climbing of the ladder itself within the turbine.
Thank you. That was a really good question and great responses. Some more. How do you think we can embed this systematic approach into the development of run-of-the-mill, in quotes, occupational health fitness for task assessment?
So that's a really interesting question, because that crosses over between the health and medical, and then those which are physically demanding based on the actual task itself. But I think when it comes to kind of the health aspects, it's understanding what those components are. So for example, in this, actually being able to have a clear range of movement around a job, around a joint, is an absolutely fundamental aspect to be able to do this. This is something that is a clear health kind of avenue that can be looked at. So good joint kind of range of movement. Another one is the ability to coordinate. So can people actually coordinate upper and lower body? So this comes very much into kind of health parameters.
And we see some of these components, particularly the mobility or coordination requirements, stepping onto the ladder from the vessel. So depending on the sea state, the vessel can be moving quite a bit, and you have to coordinate your body to attach onto the ladder in a timely manner, while at the same time judging how the sea state is affecting the boat. So a high level of coordination and indeed mobility. We see hip flexion ranges above 90 degrees required to do this efficiently. And this is something that we need to consider from a health perspective from our workers.
I mean, the great thing about doing a job task analysis and feeding it back into the employees is that actually it identifies to them what they need to be able to do. And often you see when they understand what they need to do is that they take measures to doing that. And workplaces can actually start implementing kind of health schemes to ensure that workers do maintain their health throughout their career. And job task analysis is a great way to actually identify what aspects of health do need to be focused on.
Great. One last question. Let's see. Do you see a future use of wearable sensors or monitoring systems in a form of rolling validation of critical task demands, or a rotational analysis of tasks to determine critical versus non-critical tasks? Very, very, very good question.
Yeah, absolutely. And absolutely, I do see that being the way forward, because not only will that give us constant feedback, but it will also allow us to have live monitoring of our workers as well. So especially if we're going into very stressful situations, it might look at work rest scheduling and help mitigate against some health and safety factors that are prominent in so many areas.
And I think to follow up on that from a biomechanical perspective, we have conducted some analysis here in our lab of the biomechanics of ladder climbing technique over 120 meters and the effects of fatigue on how the kinematics might change from the first 30 meters to the 30 to 60. And in particular, we see large changes from 60 to 90 meters. To use wearable technology such as accelerometers or gyroscopes and place them on individuals within the turbine itself would give us an excellent view of the demands from a biomechanical perspective of the actual climbing within the tower itself, which we certainly don't currently have within the research.
Great. Well, you gave a very fascinating webinar, both of you, and I thank you so much. And I want to thank our attendees for these very probing questions. We'll be able to place this recording on our Learn at Work YouTube channel, as well as the Learn at Work webinar series that is located on the Work Journal's website. So I want to thank both of you for taking the time to present, and for your special issue, congratulations. And I want to thank you so much, everyone, for being with us today for this Learn at Work webinar.